Hello and welcome to my video. Recently I visited a river in Freiberg, Germany, to examine the transported and deposited rocks and minerals. My initial goal was to search for gold and cinnabar, but I ended up discovering something rather unusual. Before any panic sets in, here's a photo I took during a flight in Canada showing radiation levels 3 times higher than those from the rocks in the Mulde River. An interesting question arose when I found the radioactive rocks in the river. Is it possible to detect and prospect for radioactive rocks and potential outcrops in shallow, not too deep water? And how does ionizing radiation behave at defined water depths? To satisfy my curiosity, I decided to set up a little experiment at home with whatever student home furniture I could repurpose. I picked 3 minerals from my collection, each with different levels of radioactivity, to see what I could learn. First up, we have some slag from the river. Next, a more radioactive piece of uraninite from the Erzgebirge, which I found with a nice flat surface to direct the radiation. And finally, another piece of even more radioactive uraninite, also with a clean, flat surface on top. Here you can see the setup of my experiment. First, I measured the background radiation for half an hour as a baseline. Then I measured the radiation from the rocks without water, and finally the measurements of the samples under different water depths using cold tap water. I couldn't simulate a water flow, and the tap water was free of large suspended particles and sediments, of course. My first attempt failed because filling the basin caused the rocks to shift, so I decided to do 3 separate runs, one for each rock. I filled the basin first and then used a small scoop to remove water from the surface. I recorded the measurements after 3 minutes and an observation time of another 3 minutes. While the quality of this experiment may not match that of a professional laboratory setup, I ensured quality accuracy and control under realistic conditions using the available equipment. Now I would like to show you my results. I would start with the radiation results for the slag, minimum and maximum values that you can find here for the gamma scout in microsieverts and counts per second for the Gradia code. On the left side you can find the water level, and on the right side the net water height above the rocks. And you can also find other values that might be helpful for any interpretation on the right side. But it's easier if we look at the visualized values in this plot. For the slag, on the y-axis we find the microsieverts and the counts per second on the right side, and the water level on the x-axis at the bottom. The yellow bars represent the yellow gamma scout min and max values, and the same for the radar code as black lines. First of all, if we consider the yellow bars, we can see that the values aren't really decreasing over the whole period, and that they are almost the same over the whole period, and they are not really above the background radiation, what makes it really difficult in the field to detect anything like the slag with gamma scout. There's not much difference in the values. Yeah, but on the other hand, the radio code values are definitely above the background radiation, and only after approximately 20 centimeters the values converges to the background radiation level. So this would means, or from my perspective and my interpretation, I would say that the radio code could possibly be used for the detection of the slag or anything like this radiation level. I switch to the weaker uraninite sample now. The table has the same structure, and we should keep in mind that the radioactivity of this first uraninite sample is more than 10 times higher than the slag before. This time the graph demonstrates more interesting phenomena. Let's start with the gamma scout again. When the rock is submerged, the values dramatically decrease. And consider that the alpha, beta and gamma window at the gamma scout was open. Afterwards, the values are slowly but constantly decreasing, and at the end, with a water coverage of 19.8 centimeters, the radiation values are still 25% higher than the background radiation. The values of the radio code are noticeably all the time above the background radiation. And what is strange here is that the measuring device showed me increasing values at the beginning. Such a radioactive rock, like this uraninite sample, can be clearly detected with both measuring devices in shallow water. And 20 centimeters of water are not enough to shield the radiation. Last but not least, we should have a look at the stronger uraninite rock sample. In my opinion, the most important one and most representative one for this experiment. The microsievert value of the gamma scout is relatively high at the beginning with approximately 3, and when the rock is submerged in water, the value decreases to around 0.7, and then slowly but constantly again to around 0.32 with a water coverage of 20.5 centimeters. This value at the end is still around 3 times higher than the background radiation. The radar code gives us increasing values at the beginning again, like in the measurement before. Whoever has an idea or an explanation for it, write it in the comments, and I'm looking forward to reading it. When the peak has reached, the values are decreasing, not linear but decreasing, and at the end, at a water level of 24 centimeters, the counts per second measurement is still 6 times higher than the normal background value. What leads me to the statement that radioactive mineral exploration is possible as long as the source is strong enough, and that water is not as effective in shielding ionizing radiation as I originally thought. That is the end of this video. I hope you enjoyed the scientific fun and hope to see you soon.